Okay, so now I want to do exercise 1.37, part 2. That is, we are assuming that AU plus BV is equal to W. So we're going to take some vector W that is a linear combination of U and V, or that is in the linear span of U and V. And what we want to do is figure out, are there other scalars, A prime and B prime, such that A prime U plus B prime V is equal to W. And here we are importantly assuming that A prime is not equal to A, and B prime is not equal to B. Okay, so let's think about this. So let's think about a special case. Let's think about when W is equal to 0. Okay, let's think about when W is equal to 0. All right, now one linear combination that would get 0 would be when A and B are both equal to 0. Okay, and so let's say there are some other constants, A prime not equal to 0 and B prime not equal to 0, where A prime U plus B prime V is equal to the 0 vector. Okay? Again, this isn't the answer yet. This is just me trying to think through an approach to this problem. So I'm looking at a special case, that is when W is equal to the 0 vector and A and B are both equal to 0. What would happen if there are constants A prime not equal to 0 and B prime not equal to 0 such that this equation is true? Well, notice what this means is that A prime U is equal to minus B prime V. And what does that mean? Well, this just means that U is equal to minus B prime over A prime V. In other words, U is a multiple of V. So let's just say this is equal to some constant C times V. Okay, so what does this mean? Any linear combination of U and V, so AU plus BV, really this is just equal to A times U plus B, I got that wrong, didn't I? U is equal to C times V, so really this is just equal to A times C times V plus B times V. In other words, this is just equal to some other constant, let's say D times V. Okay, so what does this tell us? Any linear combination of U and V is really just a linear combination of V, or a linear combination of U. So in other words, adding the U and V vectors together doesn't really get us anything more than if we just took multiples of one of the vectors. Okay, that's in this special case where W is equal to 0. Okay, now let's look at the generic case, a more generic case where W is not equal to 0, and see what information this gives us. So if you look at AU plus BV, this is equal to W. And let's say we also have two other numbers, A prime U plus B prime V. This is also equal to W. And again, A prime is not equal to A, and B prime is not equal to B. Okay, so now what does this tell us? Well, if I subtract these two equations, what do I get? I get A minus A prime U plus B minus B prime V is equal to the 0 vector. It's equal to W minus W, which is just the 0 vector. Let me go ahead and put an arrow there for now. Okay, so well, what does that tell us? A prime is not equal to A and B prime is not equal to B. So this coefficient is not equal to 0, and this coefficient is not equal to 0. Okay, so in other words, this just tells us, again, that U is just equal to some multiple of V. So what do we know? If it is possible, what does this tell us? If it is possible, then U is just equal to a scalar multiple of V. So if it is possible, then U is equal to a scalar multiple of V. Okay, now let's answer the question the other way around. So what if U is equal to C times V? In other words, what if U and V are just scalar multiples of each other? If we know that AU plus BV is equal to W, Can we find other constants that make this true? And the answer is yes. How can we do that? Well, if AU plus BV is equal to W, notice what we can do. We can just rewrite this equation as whoops, I got the arrow wrong here on the vector. We can just write this equation as ACV plus BV is equal to W. And now we can take A prime is equal to 0 and B prime is equal to AC plus B. Okay, and so those are different constants that make the equation true. Okay, well, so the answer to this question is there's not enough information. So if U is a multiple of V, then yes. So let me write this. So if U is equal to CV, then yes. If U is not a multiple, of V, then no. Okay, why is that? Because if the answer is yes, then the first part of the argument here tells us that U is equal to CV. Okay. And the second part of the argument tells us that if U is equal to CV, then the answer is yes. So together, the answer is yes if and only if U is a multiple of V. So if U is not a multiple of V, then the answer is no. Okay, so a very similar argument, but more subtle, is going to be used to answer problem number 3. I might make a video about that, I don't know. But this concept, what we're talking about, is related to the concept of linear independence and linear dependence. That's going to be in chapter 2, but we are already anticipating that concept, and answering questions like this is an important, or being able to have a framework to think about questions like this is an important idea that is around linear